Hello and welcome to our 39th session. In today's session we're going to be giving a quick review of the MOSFET improved theory. Specifically, remember that we introduced these two new parameters, K and M being the most important of the two, the more important of the two. And then we'll be going on to looking at the transverse electric field, the field that pulls electrons away from the source into the drain. It'll take about 1/3 of our time, and then we'll be looking at body biasing. We're going to be actually applying an electric field to the substrate. So that's something rather new and is only relevant in MOSFETs. And if we have time, hopefully we'll be able to at least start on the sub-threshold operation, and we'll probably be continuing that in session number 40. But before we get started, I'd like to play for you a really beautiful clip. It's Haydn, so whenever you think of Haydn, you think of beauty and joy and just wonder. So this is the finale to the Guitar Quartet by Franz Joseph Haydn, and we'll see you in about 2 minutes or so. Welcome back, and here is a brief outline of some of the things we'll be covering in today's session. We're going to start with a short review of the quote-unquote improved theory of the MOSFET. And whenever we're talking about improved theory of the MOSFET, we're talking about these two parameters, K and M, and they're related, but generally M is the one that is used because it's a little bit easier to use and it's more convenient. And then we'll be looking at the transverse electric field. This is quite a shift in gears here, so this is a new topic. That is the field which pulls electrons from the source to the drain, and in a regular resistive media, this would be basically constant. The voltage would change linearly as we go from one end to the other, which means that the electric field is a constant. This is not true in the MOSFET because the resistivity increases. The resistivity increases, the electric field, we will find, also increases, and the voltage changes in a rather dramatic fashion. But we'll be interested really in how the electric field changes, and we'll find that as we approach the drain, the electric field gets very large. Indeed, this is exactly what happens in a bipolar junction transistor, where at the base collector junction, the electric field is very high. We need that high electric field to pull electrons very rapidly in a BJT into the collector and a MOSFET into the drain. And then we'll be shifting gear again, and we'll be looking at this is actually just a short detour. We'll be looking at something called the body effect, and we'll see how that affects specifically the saturation region and the threshold voltage. And then, well, we'll be shifting gear again for a third time, and we'll be looking at something called sub-threshold operation, a very interesting and important mode of operation. And finally, we'll be ending with a beautiful song from the movie. Well, the movie is Love is a Many Splendid Thing, and we'll be listening to the theme song from that movie. So let's get started, and we start with the basic equation for the inversion charge in strong inversion. This is the equation we wrote for this quote-unquote simple theory. We have a channel voltage, which we must have because the voltage along the channel, if I was able to probe it, increases from 0 at the source to VDS at the drain, and it is a function of the transverse direction Y. That's the horizontal direction. So what we do when we go to the improved theory is that we break up, or we take a look at the threshold voltage, and we decompose it into its two parts. This is the band bending across the silicon at the surface, and this is the voltage across the oxide. It includes the depletion charge, and this is the part that we focus in on right here. And we're going to say that as the mobile inversion charge along the channel decreases, the depletion charge increases. And of course, they're both negative. Just one goes up and the other goes down. So this guy gets smaller and this guy gets bigger, and notice that they have opposite signs. And that is the essence of the quote-unquote improved theory. And what we did, we were able to go through all the algebra and a little bit of calculus, not very demanding, and we developed two parameters, K, the body constant, and M. K, recall, had dimensions of 1 over the square root. Is it 1 over the square root or 1 over? I'm not sure. Doesn't matter. 1 over the potential. I think it's just 1 over volts. M was dimensionless, and M is always greater than 1, and K can vary from about 0.1 to about 0.4, 0.5, where a good value of M, smaller is better, is about 1.1, and it can go up to 1.3 or so in cases which we're not terribly happy with. And we put that improved theory into our current voltage-current relationship, the IV relationship. And this is the improvement right there. If M is 1, this would be 1/2, and this would reduce immediately to our simple theory. M is greater than 1, so we have a reduction in the current because of the negative sign here, and that agrees with our observation. So this is the ID sat, which is the important current saturation as a function of VD sat. And we see that it is indeed reduced. We can basically just use algebra because we have an expression or VD-SAT. You put this expression back into here, and we get the final expression ID-SAT is equal to the coefficient divided by m. That's important. That's the improvement, multiplied by VD-SAT squared. In the simple theory, the m goes away, and it's just 1. This coefficient is present in all of our expressions for ID-SAT. And that's basically it. We're going to see m cropping up in other places. Specifically, we're going to see it when we take a look at the sub-threshold operation of a MOSFET. And the reason it always appears, or appears quite a bit, is whenever we have an increase in the depletion region width, we're going to think about m. In the very simple theory, there is no increase in the depletion width at all, and that's why m is just 1. The depletion width is pinned at threshold at its maximum value. That is not true in sub-threshold, and it is not true in the improved theory. So now that promised shift of gears when we start talking about the transverse electric field. So we start with our basic equation. You can't get any more basic than this. The current density is measured in amps per square centimeter, and this is the electronic charge. Sometimes you'll see Q, sometimes you'll see E. I generally prefer E because you can pronounce it easier. Instead of NQV, you just say NEV, and V is the velocity. And we're going to be massaging this quite a bit, probably in the next session, certainly in the next session, not in this session. The velocity, we assume, is equal to the mobility multiplied by the electric field. So there's a linear relationship between the electron velocity and the electric field. This is the guy that we're going to be inspecting and analyzing in this session. It is a function of the transverse position along the channel, source, drain. As we vary from source to drain, the electric field will also vary. Unlike a regular resistive media where the electric field would be constant and the voltage varies linearly, that's Ohm's law. Voltage varies as we go from the source to the drain, even in a resistive media. However, in a MOSFET, it varies in a rather complex way, and we'll be concentrating here on finding the variation of the electric field. Now, instead of writing an equation for the current density, I'll write an equation for the current. I could have put in JDS here because it's the current from the source to the drain. And generally, you don't do that. IDS, this is the drain current, and here we have an expression for the drain current. All I did was I took this part here, NE, and I substituted W, where W is not the depletion width. W is the device width. It's the dimension into the paper or into the board. And Q inversion is the mobile inversion charge. And of course, it also varies as Y. It goes down, and this goes, electric field goes up. So there's an inverse relationship between Q inversion and the electric field. We can see that this is the correct equation just by doing the units. The units of W are centimeters. The units of Q inversion are coulombs per square centimeter. And all these units here reduce to centimeters per second. There's actually another way to see this, which is maybe a little bit more easier to understand. Q inversion has units of coulombs per square centimeter. Multiply that by centimeters, we get coulombs per centimeter here. The units of mu E, well, mu E is equal to velocity. That goes way back to here. Velocity is equal to mu E. The units of velocity are centimeters per second. So it's centimeters per second times coulombs per centimeter works out, of course, to coulombs per second, or the units of current. Okay, so that's pretty straightforward. So we start at the source end, and here we have an expression for the inversion charge at the source end. The negative sign is due to the fact that it is, well, it's electrons. Electrons are negative. This here, Vg minus V threshold, is positive because in strong inversion, the gate voltage is above threshold, and there's no channel voltage because at the source, the channel voltage is 0. So that's pretty straightforward. We've seen that many times. Okay, so now just substituting equation 2131 into here, we immediately find the electric field at y is equal to 0, which is to say at the source, and here it sits. And again, the minus sign is not terribly important because we know that the electric field is negative. And eventually I'm going to just skip the minus sign and basically say, okay, it's magnitude. So it's not important because we know the electric field points from right to left, which is the negative direction. And we know that because the source is ground and the drain is plus. So therefore, the electric field must be from the source, or from the drain to the source, or negative. Okay, so we can find the electric field at any point y simply by taking the derivative. The derivative of the voltage is the electric field. That's what we've been doing for a long time. Volts per centimeter. That's how we measure electric field. Now the channel voltage increases along the channel as we go from the source to the drain. So the numerator here is positive. The denominator is positive because it's always positive going in the positive direction. So the derivative is positive. And I just want to stick a minus sign in there just to remind me, for now at least, that the electric field is negative. So, what do we have to find? We have to find the channel voltage as a function of y and a function of the current. So we basically take equation 2130, and instead of the electric field, we put in the derivative. That's where the minus sign here is, that minus sign there. And we differentiate, or we integrate, obviously. This should be a big C, a capital C rather than a CH. So sometimes I get a little bit confused, carried away, and I don't know what CH stands for channel. So it's the same thing. Whether it's a big C or CH, it's basically the same thing. This is an indefinite integral because we're integrating along some point y where the channel voltage corresponds to that particular position. And on the left side, we bring the dy over here, and instead of integrating from 0 to L, we're integrating from 0 to y. So this is an indefinite integral also. Stick in the Q inversion, and away we go. And basically, this is these two relationships are saying explicitly what we were saying before, that previously we were finding the current voltage, the output current, output voltage relationship, namely the IV relationship. So we wanted the output current as a function of the source to drain voltage. Here we want the output current as a function of the channel voltage. And since the current is the same, the current doesn't change. Current is constant. So it doesn't matter whether we put in VDS or VC. So that's what we do here. Now at any point, we have to put in the channel voltage at that particular point, position Y. At the source, this is 0. At the drain, it's VDS. We've seen that many times before. except here we're showing the channel voltage explicitly, and that's what we're integrating over. So if we do that, we get a relatively simple equation, 2135, and notice there's a y in the denominator because the integral on the left side, the IDS is constant, it goes out, and we integrate here, and the integral basically gives y. So this is what we have here. Let's see. Okay, here it is. Sorry about that. This is a constant, which is why we have VCY. And this is integrating the variable, gives us the variable squared divided by 2. So equation 2135 is a simple application of relatively straightforward integration. Now we want to solve for VCY. And we just basically take this guy, bring it over to the left side. And here I know I must have a minus sign here. So I'm playing a little bit fast and loose with my negatives. The IDS is also negative, so that's not particularly... if I had a plus sign here, I'd be in big trouble because I couldn't solve it. So that's the kind of reality check that one perhaps needs from time to time. If one, like me, is a little bit sloppy with signs. Okay, so this equation takes the form, it's a quadratic. We just basically put it in the quadratic form, and the constant here we call C. It's not really a constant, it's a parameter because it's a function of the variable y. So now we just use the quadratic formula to solve for VCY. And here it sits, right? And these are two lines. This is the first line, and then we simplify it, and this is what we get over here. This is the channel voltage as a function of y, and that's a big deal. So here I put in the minus sign explicitly. Here it should be because it conforms to our previous equation. And here sits the electric field as a function of the derivative. And basically all I'm doing to get 2139 is I'm differentiating VCY with respect to y. So this is the term of interest. This is a constant, so a constant goes away. The derivative is 0. I have a 1/2 here, so differentiate, it becomes a minus 1/2. That's why it's in the denominator. And then I differentiate with respect to y, this term, and I just bring down this as a constant in the numerator. So this is pretty straightforward. This was derived at by basic integration. This equation was derived by basic differentiation. Okay. Now one of the, I guess, anomalies of this expression here is because we have two positive terms, one here and the other here, and we have their difference. It would seem that for a big enough y, this term in the denominator could go to 0. And of course, if that happens, the electric field approaches infinity or minus infinity. Either way, plus infinity, minus infinity, they're both really bad news. That's a singularity, and we hope that that doesn't happen. In reality, of course, it can never happen. Now, the largest drain voltage, of course, is VDS, and that in saturation is just VDSat. So at the source, the VDSat is I shouldn't say at the source. The definition of VDSat, I probably should have had 3 lines here, just VG minus V threshold, and IDSat is the famous square law, which we've seen quite a number of times, given by this expression here. So if we substitute these expressions into 239, specifically IDS goes up in here. We find that wherever we have Vg minus V threshold, we put in Vd sat. That's why this is here. And IDS corresponds to this guy right here. A lot of things cancel out, which is nice. And we get a very straightforward and relatively simple equation. I kept the minus sign in here. It's not terribly important, really. We're just interested in the relationship between E sub y as a function of y and everything else is a constant. And what we see here is if pinch off occurs at the drain, in other words, if Vd sat occurs at the drain terminal, then at y equal L, this term becomes 1, and we get a singularity in the electric field. However, when y equals 0, this term goes away, and it's just Vd sat over 2L, and that is basically what we had previously. So everything makes sense, and that's a good thing. And of course, it's not a function of y. So this would be the case if we had a resistive channel where the Q inversion or the charge density did not change along the channel. And then the electric field would be constant along the channel. And of course, that would be the case if we had a resistive wire. That's not the case in a MOSFET. If we had this particular relationship, we would have a rather useless device. We'd have a device which is basically a voltage variable resistor, and that's not what we want. So putting it explicitly, the relationship for Vd sat at the drain, we get equation 2142, and as I think you can see, it's bad news. The L's go away, the L's cancel, the 2's cancel, Vd sat squared minus Vd sat. This is 0, and the thing approaches infinity. And this is under the condition that pinch-off occurs at the drain. Now we'll see if pinch-off occurs even to the left of the drain. Wherever pinch-off occurs, the electric field goes to 0. So if this was at some arbitrary point along the channel, say y sub whatever, but it was the pinch-off point, we would still get an electric field which approaches 0, and that is not allowed. And we'll see how we deal with that in just a little bit. And again, just manipulating this thing for y is equal to 0. That is what we're doing. That was what we're doing here, and we get basically the same thing. This is Vd sat, so it's IDS over ID sat over Vd sat, and we get basically the same equation that we had above, namely 2132. And here are some more manipulations. I'll let you read through them. They're not terribly exciting and not terribly important. Basically, whatever we do, we always get back to the right equations. So that gives us some confidence that what we're doing is not completely idiotic. So here again, we find it. Here I included the magnitude sign here because I was too lazy to put in the minus. This is the important thing. Let me go back right now to equation 2140, this guy right here. And we can graph this. It's relatively straightforward to graph in a graphing calculator or a graphing program. And what we find is that if we go from the source to the drain, the electric field doesn't really take off in the negative direction too quickly until we get relatively close to the drain. And this is kind of a schematic which shows that even if we're at L over 2 right here, we're only down by about 1.4. So it's maybe a little bit more severe than I've shown it here, a little bit more tilted perhaps than I've shown it in this schematic. But the idea is the same. It doesn't really, the magnitude doesn't really increase very much until we get very close to the drain, and then it just takes off like a bat out of hell, and it approaches infinity. So that's what we want to talk about. Now, So basically, I finally got around to explicitly saying that we know the electric field is in a negative direction. We know, therefore, it's negative. It's probably not necessary to continuously all the time putting in the minus signs. So at this point, we'll either put them in or neglect them. And hopefully we're sophisticated enough to be able to say, okay, if it's not there, we know it's negative. Okay. So more manipulations for finding V0. Again, at saturation, at the drain, every path leads to infinity. So now we want to look at the situation where the drain voltage VDS is above VDSAT. So in that case, what we claim is, and I think we noticed, we mentioned this previously, I think we gave an argument that the pinch-off point moves from the drain to the left into the channel, and that's shown here. So this is the channel, this region right here. This is the oxide. I probably should have mentioned that or shown that explicitly. This is the gate. So we have a pinch-off region, delta L, and we have a channel region here. And the demarcation is this point, L sub P. So the point is that if we put in, I probably should have done that, if we put in L sub P here instead of L, we would still get infinity. Now here's the point. It can't go to infinity. So we know that. So basically what we're saying is it goes to some very high value, which we call E critical, ECR. And for most semiconductors, especially for specifically for silicon, the value of this critical value of the electric field is about 10 to the 7th volts per centimeters. And we're going to make an argument now that the electric field cannot go higher than that. And let's make that argument and see if that makes sense. So here's how the argument goes. For voltages greater than VDSAT, namely VDS minus VDSAT is positive, I drop all of that across this region right here because this is the high resistance region. And basically what we have is two resistors in series, a low resistance and a high resistance. All the voltage is dropped across the high resistance. So the field across this region right here is equal to the voltage drop, which is the entire voltage VDS minus VDSAT, where VDS is greater than VDSAT, divided by this distance, delta L. That's exactly what we had when we were talking about the derivative, volts per centimeter. As VDS continues to rise, the numerator continues to rise, but the denominator also continues to rise. And they rise in the exact same proportion, so that E stays the same. The point, therefore, is that once we get to E critical, as we rate VDS above VDSAT, E critical is, well, it's E critical. It doesn't change. And that's very nice, but it's not particularly important. This is the important equation right here. And we saw this way, way back when in our first couple of sessions, we had this relationship which we kind of pulled out of a hat, and we said the velocity is equal to the mobility multiplied by the electric field. The higher the electric field, the higher the velocity. And that exactly is what we call an ohmic relationship. The velocity is proportional to the electric field. In Newtonian mechanics, the electric field is proportional to acceleration. In an ohmic situation, the electric field is proportional to the velocity. And the example we gave there was a really fancy car. Let's talk Tesla. I'm jealous because I don't have one. So you're sitting in your Tesla at a red light changes, boom, you give it a lot of power, and off you go, and that's pure Newtonian. 0 to 60 in, I don't know, 2 seconds, 3 seconds, whatever it is. Pure Newtonian. You're accelerating, and the acceleration is absolutely humongous. It's probably a G or better, G-force or better. But then you get up to a very high velocity, 60 miles per hour, and you keep applying that same force, and the velocity obviously does not change. The velocity doesn't change. Well, if the force is constant, you should keep accelerating. You've entered into a different region. You've entered into an ohmic region because the velocity is so high that the electric field, in this case, how much force you apply on the gas pedal, does not cause an acceleration. It just causes you to maintain the velocity. And if you want to increase the velocity, you increase the force. You step on the gas and the tachometer goes up to perhaps 3,000 or 4,000 RPM. Well, let's say you keep doing that. You keep pressing, you keep increasing E. The back force, the frictional force, the air force becomes so high that eventually, if you're going, God forbid, 120, 130 miles per hour, you keep increasing E and the velocity doesn't change. So you've gone from Newtonian, when you're sitting at the traffic light and you give it some force, give it some electric field in this case, that's a Newtonian situation. Then you enter into an ohmic situation where the force, electric field, is proportional not to acceleration but to velocity. And finally, you enter in a situation where the velocity is so high that even increasing the electric field, or if you're in your Tesla, increasing the amount of the engines turning over, you're going from 6,000 RPM to 8,000 to 10,000 to who knows what. And guess what? Your velocity doesn't increase because the velocity is just too darn high. So that is velocity saturation, and that is a big deal. Let's go back to our original equation. Current density is equal to NE, which is coulombs multiplied by centimeters per second. I should say this is coulombs per cubic centimeter, so that the J is amps per square centimeter. Now, this guy looks very innocent, but what it does is this requires that I have a square law dependence. And the reason is that N and V, of course E is a constant, both N and V are both proportional to VD sat. And that's what results in the square law. Now N is proportional to VD sat because N is just the number of charges per cubic centimeter, and the number of charges per cubic centimeter is proportional to what else? The doping density. The doping density is proportional to the gate voltage. The higher the gate voltage, the higher the inversion charge, and the higher the VD sat, because VD sat is equal to the gate voltage minus the threat voltage. So one power is in N. Now V is just the velocity, and if we have our nice proportionality here, the velocity is proportional to the electric field. The electric field is proportional to the transverse voltage. The transverse voltage in saturation is VD sat. So here's one power, here's the other power. That's where the square law comes from, right here. However, suppose we have saturation. Now this dependence of the velocity on VD sat goes away. So now I only have one power, and if I have a situation where I'm in velocity saturation, this power becomes not 2. Question is, what did I put here? Oh, this is an N. Sorry about that. This is an N. And N is between 1 and 2. Now, finally, and we're going to look at this in more detail a little bit later on, if a pinch-off occurs right at the drain, then indeed we will have a power of 2, because this equation will hold along the entire channel and only give out at the drain. However, if we have pinch-off to the left of the drain, then we have a region where this equation no longer holds, and n is less than 2. If pinch-off occurs at the source, then the entire channel is pinched off, and then we have n is equal to a little bit, just greater than 1. So n can never be equal precisely to 1, nor can it be equal to precisely 2. It's somewhere between 1 and 2, and that is why it is said that square law dependence has never been observed even in very long channels. Generally, we associate the situation where we have n less than 2 is associated with a short channel device, but even in a long channel device, n will be less than 2. And this is just a table which summarizes the different conditions for VD-SAT. This is the equation which corresponds to that, some comments and things like that. So this is the current voltage relationship. This is the electric field current relationship. And finally, we have a summary of everything we've done. If the pinch-off is to the left of the drain, that means that the source of drain voltage is greater than VD-SAT. In this particular case, we have the pinch-off at this point right here. Again, this is the gate, this is the oxide, and the channel is here. The channel length we call L prime, that goes from the source to the pinch-off point. So this point right here would be L prime, and demarcated by LP right here. And the rest of this region right here we called delta L previously. That is the pinch-off region. And what we say here is as the VDS increases, this division moves. This point right here, the point LP, moves to the left. So what happens here, and this is actually quite interesting, the channel itself gets, of course, smaller. LP or delta L, this arrow, this double arrow gets bigger. This region gets smaller. And what happens here is exactly the same thing that we had in a BJT. Remember what we have in BJT is we put a larger reverse bias between the base and the collector. The base shrunk. Well, here we put a larger and larger VDS, and what happens? The channel shrinks. Well, if the channel shrinks, it's going to work out, and we'll see quantitatively what happens, that the current is going to get bigger. And the reason is, well, it should be fairly clear if we think about it. The voltage is now dropped across a smaller distance. So the electric field gets bigger because the electric field is just the voltage divided by this distance L prime. So if L prime gets smaller, the electric field gets larger. Electric field gets larger, the current gets larger. Exactly the same thing that happened in a BJT. The neutral base region shrinks and the current went up. So when going through this exercise with the transverse electric field, we actually come to two kind of bottom line takeaways. And here they are. One is we have something called channel length modulation. The channel gets smaller. Here's the channel, L prime. As VDS rises above VD-SAT, this part here, this double arrow, this guy grows, moves to the left. And this point where the arrows meet moves to the left. L prime gets smaller, the electric field gets larger, the current gets larger. That's one takeaway. And the other takeaway is there's something called velocity saturation, where the electric field gets so big that the velocity cannot increase anymore, and we lose our square law dependence. And as they say, good riddance. You don't need it anyway. It makes the circuit designer's job a little bit easier not to have a square law dependence. So we're going to examine channel length modulation and velocity saturation quantitatively in quite a bit more detail in the next chapter. Okay, so let's go on now to something called body biasing. And actually, body biasing is the next present section, and then the next session, which is subthreshold operation, we're going to be refocusing back onto the depletion region, which we didn't really consider very much when we were talking about the transverse electric field. So first we're going to consider where we have strong inversion. The gate voltage is above threshold. So in that case, we know that the depletion region width has reached its maximum value, so that if we increase the gate voltage any further, all the additional charge goes into mobile inversion charge. And that is shown in this diagram right here. We have VG above the threshold. We're going to start with VDS equals 0. So that's why there is a horizontal line here. The thick dotted line is the VD max, and this area above it is negative fixed ions. What we don't show in this picture is that there's also an inversion charge, and we'll show that later on. So there's actually two areas of negative charge. There's mobile charge at the channel, and there's fixed ions in the depletion region. And the depletion region demarcation is horizontal because VDS equals 0. The new part is we have a body bias. We have a voltage which we apply to the back end of substrate. Now, we know that there is a circuit between the back end and the gate. That's the only way the charge can travel between the bulk and the gate is through a circuit here, because there is a big barrier due to the oxide. So if we put a bias on the gate, it's like a bias on the substrate, it's like we're changing the bias on the gate. So it's not unreasonable to think that the body bias and the gate bias will work in tandem. And that indeed is the case. One more little aspect of this. If we take this part right here and we blow it up, so the oxide is on the very top. Here we're showing the mobile inversion charge explicitly, and here's the depletion charge, and here is the bulk. Well, we have a p-n junction. We have a p in the bulk. We have an n in the inversion charge. These are both have charge densities. P was about, our default is 10 to the 17th. The inversion layer will be on the order of 10 to the 17th to 10 to the 18th, and we have a depletion region between them. These are the classic components of a p-n junction, which is exactly what we have. If we make the bias on the substrate negative, we are increasing the barrier. We're attracting holes from the bulk, or I should say from the depletion region, right below the depletion region. We're attracting into the bottom of the substrate. So therefore, we're increasing the depletion region width, and we're increasing the barrier height. It's a classic reversed bias. And we can quantitatively write that as now the Q inversion, which consists, of course, of the mobile and the depletion. We're adding negative, that's what I'm on this side, negative depletion charge. Well, negative depletion charge is equal to some capacitance multiplied by some voltage. Charge is capacitance times voltage. Well, what is it? It's the depletion capacitance multiplied by this substrate potential. So here we have the new Q inversion, and here it is, right here, and we can just manipulate that so that now what we're doing in effect is we are changing the threshold voltage. This is the old threshold voltage. We are now increasing the threshold voltage by this amount right here, C depth divided by Cox. Gosh, that looks a lot like M or K. So we're going to not be surprised to see that we have the body constant in this new theory. Okay. And one of the rationales we can see this purely qualitatively is if we make the depletion region wider, we add depletion charge here, we've got to reduce Q inversion. I haven't changed the gate voltage. So if the gate voltage stays the same and I increase Q depth, I must decrease Q inversion. In fact, I can decrease Q inversion to the point where it goes out of strong inversion, goes into weak inversion, increasing it more, it goes out of weak inversion and back into depletion. So clearly now I have to apply a larger threshold if I'm applying a negative back voltage to go back into strong inversion. And that is exactly all that this equation states. And we can see that right here by saying that the change in the threshold voltage, that is this guy right here, and basically we say it's equal to the old, the new threshold voltage, which includes the back bias, minus the old threshold voltage. Now, you say, well, where's our channel voltage? Well, we're saying that VDC, or VDS, is equal to 0. So there's no channel voltage in this part, and there's no channel voltage in this part. However, there is a body bias. So this is the new threshold. This is the old threshold. Their difference is equal to the change in threshold. And we can just carry that forward. It's pure, relatively simple algebraic manipulation. And we bring out this constant gamma, and that looks a lot like the constant K, the body constant. The difference is we have this square root of 2. But it's essentially the body constant given by equation 2113. And the same rules apply. It works out that we like this to be as small as possible, which is why we like the doping concentration to be as small as possible. That's what our equation says, and that's what our intuition says. However, it's unfortunately not the case. So it's the case for here, but we have a trade-off, a balance, and there are other more compelling reasons that we like to make the doping concentration as high as possible. Okay, now we ask the question, what does the effect of substrate biasing, this back bias VSB, have on the drain current? So far we've had VDS equals 0. So now we're going to put a drain current. We expect that the drain current is going to decrease due to substrate biasing, and that indeed is the case. In order to do this quantitatively, we use a kind of a simple trick here. Because the back bias is in series with the gate bias, we basically can push everything down. So we have, this is the prime, or the new guys. They're equal to the old guys minus the back bias. So everything is pushed down by the back bias. And now we write an expression for Q inversion, with the new values of Vg, the threshold, and Vc. We're now including Vc, and we go through the algebra. It's not terribly complex, so I'm not going to go through it in too much detail. And we do the same thing now. Again, we are integrating over the whole channel, not over part of the channel. So instead of having y here, we have L. That's why the L is in the denominator. And we get a full expression for IDS. This includes the bulk charge theory, which we've been calling the improved theory. They're both the same thing. And we see that they are identical, except that we have new terms which reduce the value of IDS even more than the improved theory did. And that's why this is negative here and negative here. So we have a reduction in IDS due to back bias, and that is reasonably straightforward. So just to summarize, everything that we've said in saturation holds and carries over to the body effect and saturation. And all we're doing here is we are giving the circuit designer another knob to push. He can now put a voltage on the body, and he can control the threshold voltage in real time, and that is a very nice added feature. Okay, and we don't have any time now to start a new topic. The next topic is sub-threshold operation, and we'll start that in our next session. So we will skip all the way down. Oh my goodness, all this good stuff. No, not that good, but it should be fun. On sub-threshold variation, and we'll go to the very end. And here it is, and we'll end with a clip from the movie, stills from the movie Love is a Many Splendored Thing. One of the lyrics I love in this, your fingers touch my silent heart and taught it how to sing. And we'll see you next time.
Love is a many splendored thing. It's the April rose that only grows in the early spring. Love is nature's way of giving a reason to be living. The golden crown that makes a man a king. Once on a high and windy hill, in the morning mist, two lovers kissed, and the world stood still. Then your fingers touched my silent heart and taught it how to sing. Yes, true love's a many splendored thing. Oh, once on a high and windy hill, in the morning touched my silent heart and taught it how to sing.